We're going to continue with chapter 23 and look at examples. All of the examples are coming straight from your example sheet, so we're just going to go from there. So the first one, which is number 2, says a company has set a goal for developing a battery that lasts over 5 hours, which is 300 minutes, in continuous use. In the first test of 12 batteries, they measured the following lifespans, again in minutes. We want to know if there's evidence that the company has met its goal, and we're going to use a 90% confidence interval to determine this. So the first thing that we have to do before we can do the confidence interval is state what model we're using and then test the appropriate assumptions and conditions, or check them. So the model that we're using is a one sample t interval. For the assumptions and conditions, there are 3 of them. The first one is randomization, where this is not actually a random sample. However, because we're just testing the first 12 that they produced. But what we can say is that it is reasonable to assume that they are representative of all batteries. Then we have the 10% condition. And again here, we don't really know what the overall population is, but I would imagine that 12 is less than 10% of all the batteries that they're going to produce. And then the nearly normal condition. Now, in this particular case, we have the data, and I didn't show the histogram here because I didn't have the space for it, but the distribution of the battery lifespan is roughly unimodal and symmetric. Now, it's not enough just to state this. We have to show the histogram using the data that we have. And you can do it on your calculator and then just draw a rough sketch of it. And this really is only roughly, but it's still good enough. Once we have checked our assumptions and conditions, we can then go on and actually do or create the interval. Our interval is going to be our sample mean plus or minus our margin of error, where again our margin of error is equal to our critical value, which is now t asterisk because we're using the student's t model, times our standard error. The first thing I need to do is I need to actually calculate the mean of all of those batteries. So I would add them all together and divide by 12. So I find out that my mean ends up being 306.25. Then I need to know what my standard error is. And my standard error is going to be the standard deviation of my sample. So I would calculate the standard deviation of those 12 batteries, which ends up being 29.31, divided by the square root of my sample size, so the square root of 12, and that ends up giving me 8.46. So the next thing I need to do is I need to figure out what my critical value is. So my critical value for 11 degrees of freedom, because remember our degrees of freedom is 12 minus 1, or sample size minus 1, will be 1.796 for a 90% confidence interval. And again, we can either use our calculator to look that up or use the table to look it up. Then my confidence interval will end up equaling 306.25 plus or minus 1.796 times 8.46. This gives me an interval of 291.05 to 321.45. So once I have my interval, I then have to interpret it and answer the question that they asked, because they wanted to know, is there evidence that the company met their goal? So are the batteries lasting for 5 continuous hours or 300 minutes? And in this particular case, my conclusion ends up being I am 90% confident that the mean battery lifespan is between 291.05 and 321.45 minutes. Because 300, that would be my null hypothesis, is inside of this interval, we would fail to reject. So because the battery lifespan can be below 300 minutes, at least with a 90% confidence interval, then we would say that no, they have not guaranteed to reach their goal yet, because it could last less than that. For the next example, which is number 3, says a radar was set up in a neighborhood to let drivers know how fast they are going in hopes to reduce speeding. One resident stood where he could see the radar and recorded the speed of every car for a 15-minute period. After observing 23 cars, the average speed was 31 miles per hour with a standard deviation of 4.25. We want to know, does this average speed exceed the posted speed limit of 30 miles per hour? Now, in this case, they're not actually asking us to do an interval here. They're just asking, does this speed exceed the posted speed limit? So what we're going to do is we're going to end up running a test. Before we can run the test, we need to state what type of test we're going to do, check our assumptions and conditions, then do the mechanics, and then give our conclusion. The first thing we do is we state our model and check our assumptions and conditions. So our model is a one-sample t-test for a mean. Our assumptions and conditions again are random, independence, and nearly normal. It's not a random sample, but there's no real reason to think that the cars driving by are not representative of all cars in the neighborhood. The next one is independence. It was a convenient sample because the guy just stood there watching, but we don't have any reason to really believe that two cars were driving near each other, so we can assume that their speeds are independent. And then the nearly normal. It seems reasonable that the data would follow a normal model. Some are going to maybe drive a little slower, some may drive a little faster, most will probably be right around the speed limit. However, it would be nice to see the histogram of the data to be able to make sure that the data is actually unimodal and symmetric. And we would have to state that when we are checking the condition. Then we have to give our hypotheses. So in this particular case, our hypotheses are that the null hypothesis is 30 miles per hour, and our alternative, we're checking to see if they exceed the speed limit. So our alternative is that it is greater than 30. After this, I need to, again, calculate my standard deviation, where my standard deviation is going to be the standard deviation of the sample, 4.25, divided by the square root of the sample size of 23, and that gives me a value of 0.886. Then I have to calculate my z-score. So my z-score is going to be my observed mean, which was 31 miles per hour, minus the null hypothesis mean, the given mean. We're assuming people follow the speed limit, divided by the standard deviation, 0.886, and that gives me a z-score of 1.13. Then I have to calculate my p-value. When I'm calculating my p-value, I want to sketch the normal model to show what area I'm actually checking. So here's 30, here's 31, and I'm looking for this shaded area right here. So that gives me a p-value of 0.136, or 13.6%. In this case, that's a pretty high p-value. It is above all 3 alpha levels that are commonly used. So then because it's high, that means we'll end up failing to reject the null hypothesis. So our conclusion is that with a p-value of 13.6%, I failed to reject the null hypothesis. There is not enough information or enough evidence to show that the average speed is in fact too high. Apparently, this person living in the neighborhood is just a busybody, and he has no evidence to suggest that people actually are speeding. So again, with this example, we stated the model, we checked our assumptions and conditions, we gave our null and alternative hypothesis, did the mechanics, and gave our conclusion. So looking at the last example, so number 5 on your sheet, we're going back to the battery example. Before, we used a confidence interval to test to see if the company had met their goal, and we decided that they hadn't. A hypothesis test gives us stronger evidence on whether or not we can actually reject or fail to reject. So we're going to actually do a test this time. So again, we still have to check our assumptions and conditions, still have to state what the model is. So in that case, the model is a one-sample t-test, and our assumptions and conditions are the exact same as before. It's not a random sample. Just 12 were produced for testing, but it's reasonable to assume that those first 12 are representative of all batteries. Then we have to check our independence condition, or our 10% assumption, and 12 batteries are going to be less than 10% of all batteries they will produce. And then the nearly normal, again, when you have the data, you have to show the histogram. But again, it was roughly unimodal and symmetric. Then we actually have to do the mechanics. So the first thing we do is state our null and alternative hypotheses. So our null hypothesis is that the mean is 300 minutes, and our alternative is that it is greater than, because they're trying to make a battery that lasts longer than those 300 minutes. Again, my sample mean ended up equaling 306.25, and my sample standard deviation ended up being 29.31. So to calculate my z-score, it's my sample mean minus my null hypothesis divided by the standard error. So 29.31 divided by the square root of 12, and that gives me a z-score of 0.739. Again, when we calculate our p-value, we want to draw a sketch of the normal model to show the area that we're actually looking for. So right here is 300, here is 306.5, and I'm looking for this area, for the area over it. And that gives me a p-value of 0.238, or 23.8%, which again is high. It is above all three common alpha levels we use. So our conclusion then states that with a high p-value of 0.238, we failed to reject the null hypothesis. There is not enough evidence to suggest that the company has met their goal of a battery life of over 5 hours. So again, in my conclusions, I'm stating my p-value, I am stating whether I reject or fail to reject, and I am putting it in the context of the situation. And note, I continue to put the context in terms of my alternative hypothesis. Yes, they have met their goal, or in this case, no, they have not met their goal, which was our alternative hypothesis. That is the last example that we're going to do, but we are going to have one more thing just to talk about tests and intervals. So confidence intervals and hypothesis tests are connected because they are based off the same data and conclusions. For example, in our battery example, we failed to reject in the test as well as in the interval. So they typically will go together. They are essentially two different ways to answer the same question. But that means our confidence level is tied to our alpha level. So for a one-sided alternative, a confidence level of C, the alpha level is 1 minus C cut in half, because we're only looking at one side. For a two-sided alternative with a confidence level of C, the alpha level is just 1 minus C, because we're looking at both sides, so we don't have to cut it in half. That is it for chapter 23. I hope you guys have a great night, and I'll see you tomorrow.